Good morning, everybody. My name is Chris Mee. I'm a professor and chair at San Diego State University. And today I'll be delivering a plenary speech at ECCE-Asia in Nanjing. I'm sorry that I'm not able to participate to this conference in person, so I'm delivering this speech via virtual mode. And I hope that the pandemic will be over so that we can all meet in person. Unfortunately, at the current time, it is not possible. So let me start with my presentation. I'm going to bring my screen share. And I'm going to start my presentation in the presentation mode so that you can see. I'm going to duplicate the presentation so that you will see better. Okay, wonderful. So the topic of my presentation today is to expand the technology and application of wireless power transfer systems. As I mentioned earlier, I want to mention that I will serve as a general chair for next year's wireless workshop. So this workshop is called WOW, Workshop on Wireless Power Transfer. It's going to happen on June 1 to 4. 2021 in San Diego, California, USA. Again, I hope that this pandemic will be under control so that many of you could join us for this conference in person. We're going to have 4 days of event filled with technical presentations, plenary. We already have keynote speeches confirmed for this event. We're also going to have a banquet at the Midway Aircraft Carrier Museum. So I'm hoping that this will be a great event after the pandemic is under control and everybody can meet in person. In fact, personally, I'm eager to go out and meet my colleagues at certain events. The San Diego is located at the southwest corner of the United States in California, near the Mexico border. The university is located about 50 miles from downtown, and the airport is also near downtown. The campus is built in La Mesa on top of a hill, and with beautiful architecture, with this Spanish-style buildings, and with the conference here, and I hope all of you can join and also visit the campus during the conference. So in today's presentation, I'll start with the principle of wireless power transfer. And then I'll dive into a little bit of safety of wireless power transfer, because without the safety and the protection of the system, we will not be able to commercialize the system at a larger scale. After that, I'm going to talk about a special circuit that we developed in our lab, including this double-sided LCC topology and also LC topology for capacitive wireless power transfer. And I will move on to the application horizon of WPT, which is the key of today's presentation. And I hope this will give you an opportunity to look at what are the applications that can be potentially commercialized in the near future. And finally, I'll give you some of my own thoughts. So let's talk about the principle of wireless systems. As many of you probably heard that the wireless power transfer has been in existence for over 100 years, starting 100 years ago with Nikola Tesla building this Tesla Tower. And for the wireless power transfer, we can name them in different ways, such as contactless or inductive or capacitive or strongly coupled magnetic resonance circuit, wireless energy transfer, and so on. If we look at the method for wireless power transfer, it can be classified into 3 categories. One of them is electromagnetic induction. The second is radiation. The third is electromagnetic resonance circuit. Within the electromagnetic induction, that has been used for a long time, mostly for inductive heating in, for example, mining and other area applications. The radiation actually includes quite a few technologies available, for example, radio waves, microwaves, and we use every day microwave to warm up food, laser, and ultrasound. Many of these radiation methods is hard to be used as electricity or efficient wireless electricity transfer because the receiving end is heat. So, so if you look at all these methods available, many of them transfer heat. Some of them can transfer electricity but with low efficiency. So the final category highlighted here, that's for today's discussion, is based on electromagnetic resonance circuits. The application of wireless power transfer is very wide, from low power, such as cell phone charging, tablet charging, consumer electronics, to human wearable devices and implants, to high power applications such as electric vehicle charging for passenger cars and buses, lighting and other applications, and so on. So principle of wireless power transfer is actually very simple. For inductive wireless power transfer in particular, it simulates the application of a transformer. Traditionally, we have transformer, but the transformer, the conventional transformer, works very well because there's very little leakage. Most of the inductance are mutual inductance between the primary and the secondary. Leakage can be as low as like 1 to 2%. So by looking at this transformer, you can see that if you apply 100 volts on the primary, only maybe 1 to 2 volts will be dropped on R1 and L1 sigma. The most voltage is applied at the main inductance. The main inductance is going to have a mutual coupling with the secondary, and the secondary will receive most of the voltage. If you have a 1-to-1 ratio here, the secondary will going to receive like 99 to 98% of the voltage, which is at 99 or 98 volts. And then you have a little bit drop on the secondary inductance, leakage inductance, and resistance. So therefore, anywhere from 95 to 98% of voltage is dropped at the load resistance, which is V2. Therefore, the efficiency can be very high because the loss on R1 and R2 is negligible. The loss at the core, the magnetic core, is also very small. So overall efficiency you can achieve. For small application, small power maybe 92%, 80%, 90%, but for high power applications, it can go as much as 97 to 99%. So let's look at what conventional transformer. As I said earlier, wireless power transfer simulated transformer. But the problem is that the leakage is so big because now you're talking about two coils that not one on the same core, but they have a distance. With that distance, the coupling becomes as low as 20% or even 10%. With that kind of leakage, you have trouble because now if we look at the same example, if we apply 100 volts of the input, 80% is dropped down L1 sigma, only 20% at the mutual coupling. And if you have 1-to-1 ratio, the voltage as a secondary at the main inductor is only 20 volts. Now you drop another 80% on L2 sigma, which means you have only 5 volts at the output, which means there's no way you can have high efficiency because the voltage drop is so much that if you want to have the same amount of power, like say 96 watts, now you're going to need, because only 4 volts, so you're going to need 20 plus amps, like 24 amps of current. And that 24 amps of current square times R2 gets you a lot of losses. So the efficiency quickly drops to less than, say, 10 to 5%. So therefore, this is not going to work. So what do we do then? Well, the beauty of the circuit is that in addition to the positive impedance that is caused by the leakage inductance, we do have a capacitor that we can use, which creates a negative impedance. Now, on this circuit, we connect C1 on the primary and C2 on the secondary. If you design the circuit such that the impedance of C1 cancels the impedance of L1 sigma, and C2 cancels L2 sigma. See what happens now when you apply 100 volts on the primary? Almost all the voltage is applied on the mutual inductance, and the secondary are going to have the same amount of voltage as you have from the primary. Therefore, you have a lot of voltage applied on V2. Now the whole system will work at a high efficiency. So you can solve this circuit with very simple loop analysis, and you can get, based on the input voltage and the circuit parameters and the load resistance, you can get the current, and then you can get the voltage, the phase angle, and power, primary, secondary, and efficiency. Now we can plot this efficiency as a function of frequency. Now I plot these 3 curves here. The 2 red curves represent 2 different design conditions. One resonant at 45 kilohertz, another one resonant at 90 kilohertz. The blue one is also resonating at 90 kilohertz, but with a different set of parameters. Now, if you look at it, you can find right away that if you design the circuit right, you can have efficiency as high as 95%. In this particular example, 90 kilohertz, 95%. If you don't design the circuit in a proper way, you can have efficiency as low as 40% with the blue curve, even though it's still at 90 kilohertz, but you get 40% efficiency. Another curve can resonate at a different frequency, like 50 kilohertz, but at 80%. So we can adjust the circuit parameters, adjust the design so that you can reach a high efficiency. That's number one. Number two, that efficiency only happens at a small range of frequency. Take the top red curve as example. You achieve 95% efficiency at 90 kilohertz. But if you drop the frequency to 75 kilohertz, the efficiency drops to less than 10%. So therefore, we have to control the circuit such that it works at the frequency you design. So the previous example, looking at the series resonant condition, C1 resonant with L1 sigma, C2 resonant with L2 sigma. That's called a series and a series. So series on the primary and a series on the secondary. Now, we know that circuit can resonate at both series and parallel conditions. So we can transform the secondary to a parallel resonant circuit. So now you have SP. At the bottom left, you have parallel and parallel resonant conditions. On the bottom right, you have parallel resonant primary and series resonant condition on the secondary. So then you have SS, SP, PS, and PP conditions for the resonant condition to happen. To build a EV charger, you need to not only just the transmitting and the receiving coils. You not only have to design the resonant circuit on the primary and the secondary, but also you have to have many other components to work. For example, next to the transmitter, you have DC to AC inverter. Some people call this amplifier. So this is a high frequency inverter will take DC and convert it into AC and supply to the transmitter. Connect to the receiver is a rectifier and a filtering circuit. And then you may have also other DC-DC converters to control the charging of the battery. Now, the DC input to the high frequency inverter is coming from the AC grid. Well, you have to rectify, you have to do PFC, and then you may have to add another DC-DC to control the charging of the overall system. So by proper design, you can see that you can have 90% efficiency on the front end, 95, 96% on the transmitter, inverter, circuit part, and overall efficiency might be able to achieve 90%, 92%, or even 93%. But when we have all the circuit available, we have all the power electronics, everything works, we have to deal with safety. Why? Because with the transmitter and receiver, we do emit a very high electromagnetic field. That field can cause many issues for humans who is sitting next to the car, for animals that can go between the transmitter and the receiver, for metals that can be left unattended on the transmitter. This all going to have a negative impact to the system. And we can look at it one by one. For example, if somebody is lying down next to the car when the car is charging, you will create a magnetic field as strong as 27 microtesla. And electric field as high as maybe 83 volt per meters. And those are the standards from international standards that you can have. Now for the system that we design, or we designed the system at 6.6 kilowatts, we didn't measure the B field, which is quite small next to the car because there's a lot of shielding effect from the car, and electric field as well. It's not as high, so which means it could be very safe for human next to the car. If it is charging, what happens if it goes inside the car? Well, we know that the magnetic field is going to be shielded by the metal because the car is mostly metal. The electric field is also going to have some impact because you're sitting inside is like a cage. So in this example, we have a magnetic field drop to less than 1 microtesla. Electric field is going to be at 3 volt per meter, which means they're all safe. If you look at the middle part, we have the guidelines from the international standards. However, animals are not that lucky because animals are small. They can squeeze in between the transmitter and receiver. In particular in the winter time, they can go there because the pets are going to be warmer than the environment. And if they sleep there for a long time, the animals can get killed because magnetic field is as strong as 1 millitesla with 85 kilohertz of frequency, it can generate eddy current loss inside the animal, which can generate heat. And we have measured that if an animal is there for 45 minutes or longer, the temperature can rise to above 40 degrees or even 44, 45 degrees, which means animal could be very well killed at that time. For metals, you're going to have even more trouble because metals can generate not only eddy current, but also hysteresis loss due to the magnetic field. And we tested a few different metals like coins, keys, aluminum wrappers, and so on. And we found after roughly 45 minutes, the metals get burned. If the metals get burned, which means they can ignite wood, leaves, paper, plastic next to these metals, which means it can cause catastrophic events. When you park your car, you think your car is a wireless charge, but unfortunately, it may be gone after work because it has been ignited by a metal. Therefore, we have to study metal and live animal detection, which is a very hot topic, by the way, at this point. And I just delivered another keynote at the workshop on wireless power transfer in Seoul in November to focus on the foreign object detection. And this is a hot topic. But today's speech is really looking at applications of wireless power transfer technology because without inexpensive and effective metal object detection system, this wireless power transfer would have a hard time to get commercialized. But some applications, it's not that difficult, and we can look at many of them. Again, before I get into the applications, I want just to look at two circuits that we have developed. The first one is the double-sided LCC circuit. And this circuit is basically looking at similar to a bidirectional DC-DC converter or unidirectional isolated DC-DC converter, depending on what you have on the secondary. On the secondary, you have a diodes only, then it's a unidirectional, but if you have also switches, it can be bidirectional. The LCC basically form two resonant conditions for the circuit. And one resonant condition is the main transmitting circuit, L1, C1, and CF1. There's another resonant circuit, is CF1 and LF1. That resonant circuit is very interesting because it forms a parallel resonant circuit. It converts the input voltage, like Vin, from a voltage source into a current source. It injects a current to C1 and L1. Because it injects a current, now you have control over how you want to design C1 and L1. You can have a high voltage at L1 instead of input voltage. It can be like 1,000 volts. Therefore, you reduce the current. Reduce current means reduce losses, means high efficiency. And another advantage of this circuit is that the power is going to change with alignment, misalignment. When the misalignment happens, the power drop, which is good because when misalignment happens, the reactive power is the same, but the real power drops, which means the circuit is not going to get damaged. But for series and series compensation circuit, a simple circuit, the power increase with misalignment happens. Therefore, the device will experience a higher stress, can potentially cause damage. We did the experiment, this was done many years ago, and we were able to achieve 8 kilowatts for the simple circuit like this shown at the bottom. We were able to achieve almost 96% efficiency. When misalignment happens, in the middle, you see 300 millimeters, and a gap, 200 millimeters. We still have 4 kilowatts of power, but 95% efficiency. Figure on the left, you can see that the power has dropped to 2 kilowatts because the gap now increased to 400 plus misalignment of 125 millimeters. But efficiency was kept at nearly 93%. And this is from DC to DC efficiency. Now, by adding the front end, the blue part on this circuit diagram, you have another 2 to 3% of loss added to the circuit. So the red one shows the overall efficiency at 450 volts battery voltage, the blue one at 400 volts, black one at 300 volts. As you can see that the system efficiency is very well above like 90%, or even 93%. At a lower power, the efficiency will drop, but overall the efficiency was capped at 70% or above. It also based on the voltage of the battery, the efficiency can be different. A second work we have done is capacitive wireless power transfer. Basically, we took the analogy between inductive and capacitive. We replaced the two inductors with two capacitors. By replacing these two capacitors, we're able to realize a capacitive wireless power transfer. But traditionally, we know that magnetic field is much strong. I know the permittivity is much much better than the ones that you talk about. Electric field versus the permittivity is much smaller, like many orders smaller. So therefore, with the space available in the car, like a 600 millimeters under the car with two plates, the capacitance is very small, like 36 picofarad. You cannot transfer a lot of power, maybe in the watts, with the way that we're doing the inductive power transfer. So what do you do then? Well, we look at this and we say, well, you know, if we cannot do anything with the permittivity, we cannot do anything with the capacitance because of limited space available, maybe we can increase the voltage. So that's number one. If we increase voltage, because the power is proportional to 1/2 CV squared times frequency, if we increase the voltage by, say, 10 times, you can increase the power by 100 times. That's that simple. Of course, we have to worry about the insulation, the dielectric between the two plates. So it cannot be too high. Secondly, we can increase the permittivity. Well, the permittivity is air. It's hard to increase any material in between, right? So that's limited. We cannot do much about it. But lastly, we can increase the frequency. Instead of using 85 kilohertz, which is defined for inductive power, we can increase that to megahertz. Now, this would have not been possible without the wide bandgap devices. So we're able to increase the frequency from 85 to 1 megahertz, or even 10 megahertz per se, if you can do that. So we increase the power by another 15 times. And finally, we add a capacitor like a C1 on the primary and a C2 on the secondary. So with this, we're able to increase the capacitance by another 2 to 3 times. So overall, we're able to increase power by 3,000 times. So from maybe 1 to 2 watts to now 3 to 6 kilowatts. So this is now capable of charging electric vehicle. In this experiment, you can see from the figure on the left shows the experiment set up with the plates and inductors, resonant inductors and inverters. And the figure on the right shows the curves that we measured. And you can see the gating curve is not so nice. But we were able to achieve 2.4 kilowatts. That was great. And with a little bit more work like EMC and so on, we should be able to achieve easily 6 kilowatts for the electric vehicle charging. So those are the two key technologies we have developed during our work. So now I want to focus on the application horizon for WPT, because as I mentioned, without addressing the safety issues, the foreign object, we will not be able to commercialize them in a larger scale. So, but a few applications may become very well viable in the near future. One of them is the bus charging. As we know that buses are different from these passenger cars, because buses are driven a much long distance, much more time per day, and they are charged. They have to be charged somehow. Right now, all the buses carry a lot of batteries, like 300 to 400 kilowatt-hour battery. These batteries have two issues. One is that they are expensive, and two, they're heavy, because you carry so much weight. Like 300 kilowatt-hour battery can be as much as a couple of tons of weight added to the vehicle. You're carrying this weight all day long. It can consume a lot of energy from the battery. So this is not very economical. It's not ideal. So what do? Well, you can design this vehicle such that it carries much less battery, maybe 60 kilowatt-hour. Then you charge these batteries at every bus stop, because we know this bus is going to stop every 1 to 2 kilometers anyway. By charging these buses at every stop for 30 seconds, we can get enough power to run between every 2 stations. By doing this, we can save roughly $100,000 to $200,000 based on the size of the battery. That's the initial savings from the vehicle. Secondly, we can save a lot of energy, and that energy savings can be converted into something like a couple $100,000 per year because the vehicle runs all day, every day. And thirdly, we don't need to charge stations anymore because these vehicles can be charged on the curbside, right, when they are driven at the bus stops. And lastly, you eliminate the maintenance. Like you don't need a crew to charge the vehicle anymore because they're charged automatically. So it's a lot of savings can be made. And I think this can be an area that will be initially commercialized in the future. Second application, we're going to look at the light rail. The light rail right now, also the low-speed superconducting vehicles are being deployed because these vehicles don't attach the rail, so they have very little noise. But the problem that you need power for onboard system like air conditioning, lighting, controls, and so on. How do you get power on the vehicle side? Right now, when you run, no problem, you have power transfer. You can have a generator, linear generator on board. But when the vehicles stop, there's no motion, then there's no power. So one way is to put a lot of battery, right? But another way is to have a wireless charging available. So once the vehicles are stopped at the buses, at this vehicle stops, and when they're repaired, when they take passengers and so on, you can have this wireless charging. So this wireless charging can reduce the amount of batteries needed on board the vehicle. So this can be very effective. A third method for these vehicles is they have a brush attached to a reel to pick up power from the reel. But the problem is that this will create noise and the brushes can get damaged very quickly because of the raining, snowy days. So therefore, it's not ideal. I think wireless power transfer is a good candidate for this application. A third application is wireless charging for AGVs. AGV stands for automatic guided vehicles. We have a lot of AGVs, like in shipping ports, inside the factory, and so on. These vehicles are running all day long. Like you go to a port and ask them to convert their diesel vehicle into electric vehicle, you're probably going to be turned down because this vehicle is running all day and they only refuel this diesel very quickly. Converting them into electric vehicle means they probably have to buy two vehicles to replace one because the vehicles have to be charged for a couple of hours. So this is not economical. EVs are more expensive. Buying two to replace one is even more expensive. So economically, it doesn't make any sense. But if we design these vehicles to be able to charge while they are operating with wireless charging technology, you don't need two vehicles. And even for that one vehicle, you don't have to store that many batteries to run like a day long. So you save on batteries, you save on vehicle investment, therefore it may be economical for them to replace AGVs. I think so. This is another application. A fourth application is charging underground vehicles. We know that this underground automatic autonomous vehicles, UAVs, they have to be charged. In order to charge them, you have a socket, right? So the ceiling and the moving them up and down the vehicle, up down the water takes a lot of time. But if the vehicle is going to be working in a certain area under the ocean, you can drop a wireless charging pad, and this vehicle can be charged while they are working or during in between their working schedule. So you don't have to take them out with water, charge them, seal them, drop them down. Saves a lot of time. So the work efficiency can be very much improved. But charging underground vehicle has some issues. The seawater can be an issue. They come back a lot, so efficiency can be dramatically reduced. So therefore, we have to deal with other issues. The charging pad can cause electromagnetic interference inside the electronics, inside the vehicle, so we have to deal with that. So we have to come up with some novel designs that can mitigate the EMC issues inside the vehicles. The next application was talking about charging the gate drivers for multi-level inverters. Why doing this? Well, for like power station application, well, you have this solid state transformers with very high voltage, like hundreds of thousands of volts. You need maybe not even hundreds, maybe even thousands of IGBTs in parallel and series connections. and each IGBT working at a different voltage level. Driving the gates of these IGBTs can be very problematic because they work at a different level of voltage. So building this long distance relay type wireless power transfer system can mitigate this issue. So you have a transmitter and you have a pickup coil for each gate, right? So they are transferred wirelessly. So therefore you don't have to worry about grounding issue, you don't have to worry about insulation and so on. So this one, so we built the prototypes and then they work pretty well to do the gate drivers. And then also people talk about cell phones, how you can charge them in space and so on. So this one demonstrates that if you design certain coils in space like this one, it's demonstrating that you have a tabletop charging in a cubic where people are sitting, but their phone can be put anywhere in that area, it will be charged. Some other applications for high power charging, like electric vehicle, like passenger cars, including those taxis, they cannot afford to charge this vehicle for a couple hours. So fast charging is really necessary. But building high power charging for passenger cars can be quite difficult because for one thing, realizing high power with that small space can be challenging. And secondly, cost can be added up to the vehicle. So economically, I don't know whether this is reasonable or not. But definitely, it does address a few issues. For example, you don't need a dedicated personnel to pull the plug for charging the vehicle, right? So that's another one advantage. Secondly, you can realize very fast charging so that they don't have to wait for hours. Maybe you can charge the battery within a matter of few minutes. There are other applications. This one talking about electrical machines. We know that for wind power generation, for example, we have brushes and slip rings to introduce power to the rotor. So for the double effect induction machine. That slip ring and brush can get damaged over time because they are running all the time. So in this application, you can have a wireless power transfer instead of a slip ring. So there's no contact. But this is rotating. So we have to talk about the power transfer frequency, maybe at 85 or even hundreds kilohertz or megahertz, but then we have to take into consideration of the rotating speed, which translates to another frequency between the stationary transmitter and the rotating receiver. Another application I'm also interested to look into is that this is for mining applications. When people go into mining area, they have to carry many like drills and other tools to the underground to do their work. The reason is that these batteries cannot be charged underground because you cannot have a plug. It will cause spark and other problem. So you have to carry them. Each drill, for example, may last 2 hours, 3 hours. So they have to carry maybe 2 or 3 drills with each shift. With wireless charging, what you're doing that we bring the cable. You already have electricity down inside the working area. Now you put this wireless charging pad, and then you have this wireless receiver on this drill and other tools. You simply put them on the drill so that you can use them. Then you don't have to bring them back up to charge and bring them down to the working area. So this will save a lot of hassle in this area. So I think this will work very well. Lastly, I just want to talk another application with elevator. We take elevator every day up and down. And we know that elevator moves by an electrical machine with a belt and chain. But have you noticed there is air conditioning something? There is lighting and buttons, other controlling devices inside the elevator. Have you wondered how do they get the power to inside the elevator? But the elevator, I know it's moving. Well, it's taking power from a cable, and that cable is hanging on top of, sometimes on the bottom of the cart. And that cable may not be an issue if you have a low-rise 2, 3, 4, 5, even 6 stories. But what happens if you have 50 stories, 100 stories? That cable can be extremely long, and it can be fragile. It can be damaged over time. That becomes a maintenance issue. So if we have a wireless power transfer to transfer power from the hose, like the tunnel, to inside the car, basically, look at this example. We have a transmitter on the side, and then we have a receiver inside the car. And you transfer power when the car is stopped. You can build this at every level, or you can build them, where, like the ground level, where the elevator stops most. Of course, you probably need some batteries on top of the car, so that make sure when there's no wireless charging, you still have power. But this can be very effective. You can eliminate the long cable for high-rise building. That will do two things for you. One is that you can reduce the drag and the friction so that you can increase efficiency for the overall system. That's an advantage in the long haul. Secondly, you reduce the maintenance because you don't have to look at the cable. You don't have to replace them once in a while. So this will be much more cost effective in the long run. Therefore, I think this can be a very well potential application. So finally, I just want to mention briefly the objective detection in wireless power is very important, especially for high power applications. And I think eventually in our laboratory, we have developed some method for MOD and LOD using some specially designed detection coils and detection system. And we have the coils and we overlap them on different layers so that we also eliminate the blind spots. And in our experiment, we have found that this system can be very well designed, as effective as like for small 1 cent US coin, we can detect them with a 40 to 80% change in output voltage. And of course, we have to have many of these small coils designed, and we have to have an amplification circuit. We have to pick them up. And so this circuit shows 25 coils, and we have in the middle, you have to pick up circuit, and this actually pick up circuit PCB board you can see. On the right hand, top right, you see the coils that are overlapping each other with this 4-layer design. At the bottom, you see the effectiveness of each coil. And apparently, they're not the same because they're at different places and they have different sensitivity. So finally, I want to say that WPP is enabling technology for many applications. And it is still evolving, both in terms of topology, in terms of FOD, in terms of application scenarios. Both IPT and CPT have a unique application fields, and some may be for high power applications, some may be for low power applications. Other technologies, microwave, laser, ultrasound, are also studied, but apparently they are only applicable to certain applications, mostly for low power. Safety is a major concern for high power systems. So when some people talk about Tesla-free world in the long future, it's not likely, in my opinion, but the dream of Tesla will not be realized in any time soon. Like you can transfer power wirelessly without cables. So in overall, there's compromise between cost, safety, efficiency, and many other factors for commercialization. And we have to pick the area of application that is most applicable economically and safely. So therefore, that is my technical presentation. And I want to share with you, we have quite a few books published, especially working with Dr. Ring. He's contributed a lot to this book with wireless power transfer. It talks about the wireless transfer in many aspects, including the topology, including control, including theory, practice, and object detection. I want to thank the sponsors. Without their support, we would not have been possible to achieve many of the technology breakthroughs in our group. So thank you very much. And I also finally want to thank all my students for their hard work. And with this, I want to conclude my talk. And right now, this is recording, so I won't be able to answer your questions because I don't know what question you have. But when the event is happening in end November, early December, I'm hoping that I'm able to join virtually so that I can answer any question you have. But in the meantime, if you have any other questions, welcome to get in touch with me by email. And my email is on the PowerPoint presentation in the beginning. And Again, thank you for listening, and I hope you enjoyed the talk and you enjoyed the conference. And I'm hoping also by the time you see this presentation of pandemic is towards to be controlled. And I want to look forward to meeting you next year in San Diego at the Wireless Power Workshop in June 1 to 4, 2021. Thank you very much. Enjoy your life. Enjoy the conference and be safe. Bye-bye.